Hi everyone, this is Natalie Nakamura. This is my senior project IET 400 final outbrief. So I decided to do a model walkthrough in lieu of a PowerPoint since I was probably going to just take screenshots out of my model and throw them in a PowerPoint deck anyway. So we'll use the model itself as a discussion point and take digital transformation very seriously. So what you're seeing here is the descriptive model that I developed for my final project. As you can see, it's done in Magic Draw 2021X, which is a demo license version. So there are some constraints. It's kind of a hybrid Frankenstein monster of SysML, which is system modeling language, and UML, which is universal modeling language. So a little bit of a systems engineering / software engineering baby here. And so basically, I posited in my final project that a factory could be decomplexified, similar to a weapon system, whether it was, a tank or an automotive, variant, or an airplane or a spacecraft. We use systems engineering analyses on labs and other facilities. So why not apply it to a factory as a system? So basically, these analyses and model-based systems engineering exist to decomplexify problems and make them more easy to solve, especially in this age where, there are so many interface requirements, there's Internet of Things, there's complex system of systems. In order to manage all that complexity, we have to use something like a modeling language to fully understand the problem. So this model has been developed with a vision in mind to support someone like a factory manager who's going out and has to start procuring tooling or hiring people or determining like what the cost centers look like, or what new technologies he or she wants to invest in. So basically, this descriptive model exists to kind of help decomplexify and get inputs from subject matter experts across, different domains. So unfortunately, I'm not a factory subject matter expert. I am a systems engineering manager. So this model has to be taken with a grain of salt because I did my best and get to go through a peer review process. And so going through the literature review, it's very clear that, there have been some forays into modeling factories. Actually, in Germany, it seems to be very common. However, this is relatively new, being able to model a factory in this way. So what we're going to see here is an application that hasn't really been explored. Some of the the literature articles that are published kind of talk about how companies are not really willing to invest in the skill sets and the time and the energy it takes to develop one of these architecture models. Typically, so where I come from with Department of Defense programs, the government pays for these things, but if you're working commercial, or you depend on commercial revenues, or using profits to do R&D, I can see that companies would be hesitant to invest in this sort of capability, even though it could be reused multiple times depending on how many factories you might be standing up. But that would be the primary constraint. So we have me, Natalie, just creating this model myself. So again, it's not going to be perfect, but it is a good exercise of what it might look like to create a model for a factory manager, and how that factory manager might be able to use it to start hiring, or right sizing the factory. So over here on the left hand side, this is called the containment tree. It's where all the model elements live. As you can see, it looks like a database. There are also relationships between model elements where you can formalize using your modeling language, how things talk to each other, and you can export this information and flow it downstream to other factory built tools, such as if you're using Siemens process simulate or plant simulate, you're using another tool to start laying out where your tools are going to be. Well, you won't have to start from scratch. You have all your context, assumptions, and requirements in this systems engineering model that you can use. Okay, so what we're looking at here is the Start Here page, or a dashboard or landing page, which presents the information in an upfront way, kind of like a PowerPoint deck. So here we can see 4 key pillars of our hybrid SysML UML model. So we're going to talk about the operational architecture domain, the functional domain, some requirements, and then how we allocate the requirements and functionality to a logical breakdown of a factory system and its subsystems. So I'll start here at the highest level, which is the operational domain. It can also be known as the mission domain. And so that just means, we're decomplexifying and describing exactly what a factory needs to do in order to be successful. Typically, this is given to us by a customer. So the customer will say, hey, I want this done. I want this capability at this time. Well, since a company is responsible for developing their own factory, we get to do this ourselves. So you can see there are 2 key use cases that include sub-use cases. The first one being manufacturing the aircraft, and then provide manufacturing support, which is all the other supporting functions. So as you can see, again, I did this myself in a vacuum. Typically, as part of the normal model-based systems engineering process, we would have multiple stakeholders and peer reviewers reviewing this and providing inputs. So this is just directly what came out of my brain over the course of my USM academic career. So as you can see, there's key contributors that enable these use cases that, the relationship is they're dependent on these humans to help execute these use cases. And then we have what we call external performers as well, denoted in black. So we have 3, we have suppliers, customers, and auditors. And so the whole point of this is to make sure that the production manager or the factory manager is successful, right? So we're telling the manager, here's who's going to come in for which particular use cases. And of course, in order to be successful, we can't just think about the internal system itself. We have to think about, dependencies on external actors. So for instance, if my mission is to manufacture an aircraft and deliver it to a customer such as the Navy, the Army, the Air Force, I'm going to have to get auditors involved, make sure that I'm abiding by approved processes. So this would be someone like Defense Contract Management Agency, DCAA, which is the accounting arm. We have to make sure that we're abiding by these external performers rules, right? Otherwise, we're not going to be successful. In addition to that, if we're building a factory that's going to build complex, weapon systems or aircraft, commercial systems, we're going to be dependent on thousands and thousands of suppliers. So we're not going to be able to make every single piece part. We'll have, folks sending clicos or building massive wing assemblies. And so the suppliers cannot be discounted at all. We have to make sure that we understand who's contributing to what in order to be successful. So as you can just see, this is our use case context diagram. So if I hop back, the next step would be to do an analysis on the descriptive modeling we just completed, right? So as you can see, here's across the top, all of the operational use cases that I just introduced. Here are all the actors, and then you can see that there's certain types of actors that are required for every use case. So for instance, production management, you definitely need a management team to execute every one of these use cases, right? So this would be a good note to send over to the factory manager, say, hey, like obviously if you're setting up a factory for the first time, you're going to want a highly experienced production management team. You're going to want a diverse team that can work across multiple different areas. Maybe you want to have like a rigorous leadership development curricula so that you can rotate managers across different areas. And then beyond that, you can see that the next most used skill set would be engineering. I made a little note here. So engineering is very, very diverse to begin with. You might have design engineering who's developing parts, manufacturing engineering, which determines like the build plan, industrial engineering, who determines like rates or cost center allocations or utilization rates, and then tooling engineering, who might actually be buying developing custom built tools, or calibrating tools. So obviously it makes a lot of sense that you would need a diverse set of engineering staff in order to be very successful across your mission areas. Additionally, logistics is also up there. See, we have 5 dependencies on logistics as well. So in these complex environments where we're constantly moving assemblies or coordinating, different types of parts from outside suppliers, logistics is going to be very important. And if you have large assemblies, you're going to need folks who know how to drive cranes, or perhaps folks that can drive a golf cart to get people around if it's a big factory. People who know how to tag parts or sort parts or warehouse parts, this makes a lot of sense, right? So this is something that we would send over to the factory manager and say, hey, in order for you to be successful in all your mission areas, here are the top 3 skill sets that are going to have to be very reliable in order for us to be successful. And then of course you have other different types of skill sets down here. But they're a little bit more focused, and they don't probably have to go outside their swim lane as often. Okay, so that's the first domain. So now we're going to hop over to functionality. So in systems engineering, what we usually do is we like to describe how the system needs to behave in order to accomplish the mission. So I broke down into the first level of functionality. So assemble aircraft, receive and move assemblies, protect the workforce, meet customer schedule, and meet quality standards. So these are things that our factory system needs to do in order to accomplish the mission. So this is our high-level functional hierarchy. So what I'm going to show is one of those functions. And so here we have what we call an activity diagram. And so meet customer schedule. So if we're going to meet customer schedule, and I kind of touched on this a little bit earlier, it's up to us as a company and an organization to figure out what the factory looks like in order to meet the customer demands. Because usually the customer comes to us and like, hey, I want this aircraft. I need it to be capable by this year, and I need 200 of them. And so from there, we take that and then we, the prime contractor, determine, okay, so here's the design solution that will give the customer the capability they need, whether it's a helicopter or a tank or a fighter jet or a bomber or whatever. And so engineering will take that proposal, develop a concept design. And then again, this is a very diverse set of engineering functions. Manufacturing engineering will develop an aircraft build plan. And then production management eventually takes all that information and then racks and stacks it and comes up with, a plan for the factory systems that would be needed in order to meet the customer demand. So here we have, production management, and that might include, your industrial, analysts, and then come in, determine, what's a doable production rate. Of course, you'll need information from your scheduling team, and the schedulers will need to work with your supply base to make sure, if there's long lead items, what exactly needs to come in when, what your critical path is, et cetera, and see what's in the realm of possible before you actually end up with a suitable aircraft factory spec that's going to help you meet your customer schedule. But as you can see, we've allocated in swim lanes different functionality to different actors. And so this is not a typical way of doing, systems engineering analysis, but this is a good enough demo license example of who needs to do what in order to be successful. So this is just us breaking down the functionality of meet customer schedule. We're allocating out who needs to do what in order to be successful. And then I'm going to hop back and give another example of the more fun activity diagram, which is assembling the aircraft itself, right? So you'll see, again, a similar breakdown of the last activity diagram. So you have your swim lanes across the top, the owners of the activities down here. So when we're assembling an aircraft, this assumes that, we work through the proposal, we have a design solution. So engineering is going to release some sort of engineering drawing, release the build instructions that go along with it, hand that off to technicians. But of course, the technicians can't just take that paper. They need parts. They need those parts to be provided at the right cost center. And then, of course, the technicians need to be trained appropriately. They construct the assembly. They verify the assembly with the help of quality control and sell it off, and they send it to the next cost center. So again, this is just a way of decomplexifying this one action of assembling aircraft, seeing who exactly needs to do what in order to be successful, what the right order is, because we needed to capture the sequences. Maybe there's giver receivers. Obviously, in order for everyone to be successful, you need to know what you're receiving from the predecessor tasking, and then who ultimately your customer is, right? Because downstream, they're going to be waiting for you to finish your tasks before, in the proper sequence of things. Okay, so after we do all this functional analysis and start breaking down the lower level functionality, we can go back and actually tie back to the mission, right? So across the top, we have our functions that we just went over, and then we have our mission use cases from the very first operational domain that we talked about. And as you can see, we're just making sure that there's a number in every one of these matrix boxes to make sure, okay, so do we have the right functionality? Do we know exactly what we need to do? Is what we're going to do going to accomplish the mission? And so you can see that there's high coupling on receive and move assemblies. And so that means that we're highly dependent on this functionality, receive and move assemblies, in order for the mission to be successful. And so that makes sense because obviously there's going to be a lot of work in progress before you can actually assemble and deliver an aircraft, right? So there's a lot of teams that are going to be involved in the development of lower level assemblies, getting customer feedback, getting supplier inputs. So it does make a lot of sense that even though you're making all your revenues when you deliver that aircraft and the customer signs off on it, as a factory, the behaviors and the functionality associated with work in progress is very, very important. Okay, so those are the first two domains, kind of abstract if you're not used to it. But now what we can go into is the requirements domain here. And I kind of focus on a certain type of requirement. So we have different requirements out there, whether it be performance requirements, functional requirements, design constraint requirements is what we focused on because it's a little easier to conceptualize. So if we go here, did some quick Google searching, understood that there's about 12 different buckets of regulations that apply to factory systems. So as you can see here, distribution and shipping, ESO, governance, human resources. So these are buckets of regulations and rules, whether they be like ISO standards or OSHA standards or anything like that. And so we can capture these as constraints, right? Because you don't want to just build the fastest, best factory system if it's going to be cutting people's heads off, right? So we need to constrain the system in the ways that make sense so we don't get sued. So as you can see here, went in, ingested these constraints, and then constrain their specific subsystems, as you can see here. So I'll give an example of how we allocate these constraints to the different logical elements in just a second. So ESO is a good one, environmental safety, occupational hazard. So it makes sense, right, that this would apply to literally everything, because you, first of all, need to protect the environment, but you also have to protect your worker health, have to be safe, have to provide metrics to regulatory authorities. So obviously, this is going to apply at the highest level. So the aircraft production system is the highest level, and then it percolates down into all the sub levels you can see here. So this constraint applies to literally everything. So very important. So this is like an all-encompassing constraint. This is what we use the system model for, so you can inherit those constraints at lower levels. So if I were to go to a different, less constraining regulatory grouping of rules, so labeling and packaging. So you can see that in this relation map, it's like a lot smaller because obviously labeling and packaging might not apply to everyone, especially if it's like a technician turning a wrench or something like that. So obviously you're going to want your tools to be serialized. You want to have your inventory serialized. You might have RFID tags. You might have drawing numbers. And so it makes a lot of sense, right, that you want labeling and packaging relevant to the things that are only specifically being constrained by that compliance aspect. So rather than, environmental health and safety, which applies to everything, you definitely want to focus in on things that matter. So the physical stuff. So that's the requirements domain. And then last but not least, we have the logical breakdown. So this is, again, another abstraction of what the production system looks like itself. I took a little inspiration from our Groover book, from our automation elective class. And so you're seeing like a theme, right? So facilities is one area of breakdown, and then support systems. So it's kind of like having a soldier in the army. For every soldier that's out there on the front lines, you have 10 people working in the background that are supporting that soldier. So it's the same, right? It makes sense that we have technicians, but also 10 buyers, schedulers, inventory managers, engineers, whoever else, in the background, making sure that the technician gets whatever they need, even though they're the only ones that are actually putting the aircraft together. So as you can see, the inheritance of different compliance areas. And then you can see, how it breaks down. And so why is this important? And again, so if I'm a factory manager and it's my job to go out and hire someone who's going to be my facilities manager, I have to make sure that they know what their responsibilities are. So if they're the facilities managers, well, they have to work the logistics and control systems, factory plant layout, tooling. Here's what their org chart is essentially going to be, right? So as a leader, this is very, very helpful that I can get the insight that I need in order to make sure that my team is successful. And again, it is very, very complex. This is easier to read than, a Word document or a paper spec. So this is really the value of model-based systems engineering, is using a formalized modeling language and the appropriate relationships, the appropriate model elements, do this analysis. And it really starts the conversation, right? Because this is just my interpretation of breaking down the logical subsystems of a factory. I'm sure that when you look at this, you think stuff is missing or stuff is wrong, or why would you have an inventory management system over here so distributed from logistics and control systems, right? So this is where we can start having those hard conversations as an organization and understand, hey, maybe we shouldn't organize this way. Maybe we should conglomerate all the global supply chain folks into one organization. Maybe it's better for skill management and training and collaboration. So this is just an example of exposing unknown unknowns. It's also a great way of making sure that folks know what exactly their responsibilities are. So again, if we hop back here, so I always know that if I need to acquire compliant parts, the buyer is going to go out and do that. It's their responsibility. Because if you don't have anyone single point that's responsible, then essentially no one's responsible. So this is a tool, right, for exposing, but it's not actually going to help you execute. It's just going to give you the information that you need to be successful. So all in all, I think that this was a great exercise. I think that model-based systems engineering is indeed applicable to the factory subsystem, even though it's like a completely different realm of engineering. And so I think that in terms of methodology, being able to leverage, my experiences as a systems engineer in an aerospace firm, I've been, blessed. And I think this is a really cool thought experiment to go through and think about, the factory as a subsystem. Sure, it doesn't fly, but it has to be certified. And it represents just a huge, huge investment on a company's part. So I think that any company would truly benefit from, thinking through, what the factory needs to do in order to accomplish its mission. So that is it for me. Feel free to reach out if you have any questions on the content. Thank you and have a great rest of your day. Bye.